Next up we have Edward Ballas and Chris Spears, who are going to talk about the evolution of services and architecture and Internet 2. We made reference to R&E yesterday and Joint Techs, and those guys are a lot closer to these networks than we are. But in reality, if we look at how these guys are using technology, they probably are one of the largest users of 100 gig at this point. They're definitely the largest user of SDN who talks about how they use it publicly, whereas a lot of the other users of SDN technologies don't talk about it at all. And so it's a great pleasure to hear about this kind of stuff in this forum. So, thanks, guys.
Hi, hello. My name is Chris Spears. I do network planning for Internet 2. I'm going to talk real briefly about the Internet 2 architecture and really the evolution of the underlying infrastructure over the past decade and a half, and then pass it off to my colleague Ed Ballas, who will talk about one of the interesting things that we're really doing on one of our networks. So this is a real brief primer on what Internet 2 is. If you don't know, we are a national research education network. Around the time that the NSFNet was being privatized, a bunch of research universities got together and said, we really need a network that serves our needs. So they got together and formed Internet 2. I'm not going to talk about what a research network actually is. Other people have done that from this very stage. In 2011, Kevin Oberman from ESNet gave a very good presentation. I include the link there so you can go take a look at his overview of research networks. Boils down to a different set of needs among researchers, scientists, and not just big data, but more of a big science as a real driver for this. And of course, you can get more information at the link below. So I put this next slide together to try to give an overview of how things have changed and evolved over time with the Internet 2 network. And it's a little fuzzy in places, but I think it gives a good overview of really the change that's happened over time. And there are two major inflection points there where we made major architectural changes, and I'll go into detail on those in just a moment. So IP services, everybody has IP services. Well, we've had just not V4 unicast, but we've been doing multicast and V6 since 1999 when we had our first OC48 network. We had a partnership with Quest where we actually launched our first nationwide backbone. We upgraded that to OC192Cs later and then 10 gig. And then the first big inflection point came. We partnered with Level 3 and Infinera, and we actually deployed a 13,000 route mile network around the United States on a single 100 gig DTN layer on the Infinera system. It gave us a 10 by 10 100 gig capacity throughout the country, and that allowed us not only to go beyond just single 10 gig internode links, so we went to 20, then 30 gigs in between certain nodes, but allowed us to use the remaining capacity to try out different things, to build out different networks, to try different topologies, and really see what we could do to support research in different ways. We even actually set up a peering service that runs today that many of the people in this room actually peer with. The next big inflection point came in 2010 when we were the recipient of an NTIA Broadband Technology Opportunity Program grant. And in 2011, we began building what is now our current optical infrastructure, and that has allowed us to scale at over an order of magnitude what we can actually do and what we can build out. So the optical network that we have today is almost 16,000 route miles of dark fiber throughout the country. We have over 50 optical add drop facilities and hundreds of amplifier sites throughout the country. We selected the Sienna ActiveFlex 6500 platform that gives us 8.8 terabits of capacity on every link. So we can put 100 gigs on 88 channels on any internode add drop link. We have directionless capabilities in our metro areas. And we did something very unique here, and this is something very unique to the research and education community. We partnered at a very basic level with ESNet. This is the Department of Energy's Energy Science Network. They have a share in the common optical infrastructure and the spectrum itself. So we partnered very deeply with them on this. And that has allowed us to drive 100 gig penetration. We have, I think this was a count from last week, 172 100 gig transponders deployed on our network right now. These are all coherent receivers using DP-QPSK modulation. And we have dozens and dozens of 100 gig E 802.3 BA compatible 100 gig interfaces on our layer 2 and layer 3 devices connecting to this. We also didn't deploy any native 10 gig on this network. So this is an uncompensated fiber network. We didn't want to have any 10 gig outside of some of the metro areas. So we actually deployed 40 gig muxponders, and we do OTU multiplexing to get 10 gig capacity onto the network. And we've done a number of 100 gig firsts. So we did the first transcontinental in North America, 100 gig in October 2011 from New York to Sunnyvale and actually up to Oakland. And we just announced yesterday the first transatlantic 100 gig clear channel from New York to Amsterdam. So that press release just went out. So at layer 0 and layer 1, this network has allowed us to evolve quite a bit more. And as I said, we partnered very heavily with ESNet, so their infrastructure rides over the Internet 2 fiber infrastructure. But we also provide backbone services for NWAVE, which is the NOAA nationwide network. We provide services to Genie, which is the NSF-funded project for sliceable, scalable architectures that researchers can build arbitrary topologies on. We also implement the Large Hadron Collider's open network environment in the U.S., and we provide facilities for Exceed, which connects supercomputing facilities throughout the country. So we couple ourselves with our R&E partners very tightly, all the way from dark fiber, sharing of spectrum, to sharing of OTU multiplexers, and then further up the stack in a way that you don't really see in other areas, other arenas, and that allows us to do a lot more. Innovating together is one of those things we like to call it. But it also gives us a lot more for our own networks. So Internet 2 actually runs a lot of its own networks, and some of the other things that we've done, and I'll say this slide sort of represents what Dave called the SDN continuum, things that we've been doing over the years. So we have a history of experimenting with new technologies. And we've been doing dynamic network services that are driven by software, and I don't know a better thing to call it other than SDN. So Genie is one of those things that's a sliceable network substrate that we run on top of the network, and we work closely with the Genie project office. The first Internet 2 network that we built that was sort of SDN was a 22-node Siena core director network that we built on OC192 rings throughout the country. This is on the Infinero substrate. And it was programmable in that you could dial up circuits on demand, OC12s, if you want to do anything like that, and just sort of build on-demand guaranteed capacity across the country between researchers. We sort of merged that in to our IP and MPLS layer when that got robust enough, and we built in we call the Internet 2 on-demand system is ION. And you could dial up on-demand MPLS pseudo-wires with guaranteed bandwidth. So if you needed 2 gigs of capacity between one researcher and another, they could actually dial that up. And it used the Oscars IDC protocol. This is interdomain control, so you could actually get it from a lab all the way to another lab. So it really allowed these researchers to do things they couldn't do before. It made networking simple, right? And that's what it's supposed to be, because that's the only way they're going to use it. We actually have a nationwide 10 gig OpenFlow testbed that we have deployed, and I think we put that out early 2011. And the real sort of centerpiece right now, and Ed's going to talk a little bit about this, is our advanced layer 2 service. And that is our nationwide 100 gig backbone. Today there are 18 nodes deployed. That's a mix of Brocade MLX C16s and Juniper MX 960s. And by the end of this summer, I think probably September timeframe, we'll have 25 nodes deployed throughout the country, all connected at 100 gig. And this network was built as an open exchange. This is the sort of glossy map, but it gives a good representation of our fiber footprint throughout the country. The layer 2 and layer 3 nodes on the network are not quite representative. Again, this was put together by our marketing people. But that's the underlying fiber infrastructure. So ESNet's built on top of that, NOAA's built on top of that, Internet 2 networks are built on top of that. This is the Internet 2 networks. So this is our layer 2, our layer 3, our peering service, our international connectivity. These are the things that Internet 2 itself runs and not our partner networks. So while long ago we had just an IP network that was 11 nodes connected by OC48s, we've grown quite a bit just in what we operate ourselves over the past decade and a half. And with that, hand it over to Ed.
Hi. So some of this I'm going to talk about is sort of a follow-on to some of the demos we did at the NOG lab down in Orlando. Much of it's the same. There's some additional data about availability and whatnot that I'd like to cover today, though. So Chris kind of talked about the history of SDN and covering a variety of different networks from HOPE to AL2S. And really, I want to touch on that again just to show, the key thing we're striving for is this idea of programmatic network control, whether it be at layer 1, 2, or 3. We're trying to figure out where we have good touch points, what's sane, and what we can do for our customers. And the motivation really comes down to, we really want to give the members the ability to directly create communication pathways between their research facilities or their supercomputing sites, whatever it might be. We want to remove ourselves from the critical path in terms of provisioning delays, so we want to not have to call the NOC, that kind of thing. But in general, with any of these kind of things, we want to be cognizant of issues related to quality and control in terms of, when we talk about control, it's a matter of don't burn down the network by adding some feature that's just irresponsible, right? And the major use case for us is this notion of national exchange fabrics. And the idea there is we want to give our customers the ability to set up their own networks, not have to go through our IP network if it's not considered suitable, right? So Internet 2 and we all love our marketing people. They have this idea of what they call the Internet 2 Innovation Platform. This really constitutes the AL2S network, is what we like to affectionately call it. The key ingredients for this really are big pipes. So this is 100 gig with minimal aggregation. So if you have elephant flows, they work well with 100 gig. That's the idea there. But we also want to combine that with an open networking stack that in some way provides an ability for non-vendors to sort of innovate. That's one of the concerns we have with traditional approaches, is that the vendors control the pace of innovation, right? And we also want to encourage domain experts to get involved in the process of creating these new services, and I'll get into that in a minute. And then the other key ingredient really is technical means to separate experimental network research from production research traffic. I'll get into that in a minute. But our goal is really, to recap on the objectives here, are to improve the experience for their R&E users. So, those users include people that do network research and do dangerous things, but it also involves people doing fundamental science that are moving large data sets, and we'd like to be able to have those two coexist, right? And ideally what we want to do is find a way to make it easy to fill those pipes and allow scientists to focus on discovery, not on sort of the logistics of data movement. The enablers for us right now, we are and have been looking at OpenFlow 1.0. We are eager to see what we can do with 1.3. But in general, we're not really sort of partisans here. Any decent cross-platform SDN technique that we can get a hold of that'll help us, we're willing to entertain, right? So the platform itself has three main parts. It has a test lab where we have about 8 switches and 6 PCs interconnected with a MEMS device that we can do programmatic control of the layer 1 topology. And we use something called Jenkins to do sort of test automation. So as we bring in new applications or services into our environment, we first bring them into the test lab and run them through their paces there. From there, if they graduate out, they go into the NDDI network. This is an older network we built a few years back with 5 NEC PF5820 switches. These are OpenFlow switches. They're configured in a ring, and it's a 10 gig network. The key here is we can do at-scale sort of prototype testing of new services, and we can actually then route live traffic onto that and see how it reacts to sort of stress testing. And then from there, if everything goes great, we move on to the L2S network, which Chris already described. And today at this point, we have one major production service, which is this thing called OESS. And this provides those sort of end-user controlled point-and-click provisioned pseudo wires. So we demoed this last year at the NOG lab, or excuse me, the last NANOG. And so I don't want to belabor the point too much, but really the key of this service is that it represents us implementing something in OpenFlow that had already been implemented in the ION service. So it was an existing use case. It was dead simple, and we knew our community wanted it and needed it. So what this allows them to do is they can go into this application and they can configure pseudo wires from any endpoints that they or their agreed upon sort of partners need, and they can provision a pseudo wire and at 2 in the morning. They can specify the path. They click go, and a second later, they're forwarding traffic. They don't need to call the NOC. They don't need to set up a maintenance window. Away they go, and it's instant gratification, right? So that's the idea of OESS. So one of the things I do want to talk about really quickly was what the innovation platform is not. So I know there were a lot of questions at the last NANOG about what this thing is. So the first thing it's not just a playground. We're fairly risk adverse as much as you can be with such a technology. I mean, I realize that's all relative, right? But we do encourage responsible experimentation, but the process to get things into our network is actually fairly involved. It's a three-step process, as I described, and we're not really inclined to just let anybody in there and with a wild hair idea. The idea is that we take managed risks, right? And so there's a process behind that we use to mitigate the risk. And it's also not just a test bed. We do at-scale operation of OpenFlow apps. So the OSS application is something right now. One of its primary use cases today is for customers that do backhaul into the layer 3 service, and those customers are pushing greater than 10 gig at times, and they depend on this. And so this is a production quality service. And there are of course other uses for it. For instance, creating pseudo wires for other experiments. But we know there are risks, and we're trying to manage them, and that is never a perfect thing, but we do the best we can, right? So when it comes to what happens next, so we have this OASS, and great, okay, it's controlling the switches. So how do we actually run multiple different applications? And this gets dicey, right? So this is this notion of multi-tenancy. We can't really create a dedicated production network and a dedicated sort of research network. So we need to have a network that supports both use cases because we don't have the money to do both independently. And so what we really want to do is figure out a way of having a production platform that can provide, sort of multi-tenancy capabilities so that we can build some sort of virtual networks on top of it. So we want to be able to run multiple applications on this network, and we also want to not have to trust these applications, right? Much in the same way that if you had a server and you wanted to create virtual machines that you provide to your customers, what we want to be able to do is to our community members is provide virtual networks, almost like, think about it as a VRF on steroids, where they have full open flow control, and they also have topologies and whatnot. But we can just give them basically that virtual network and let them run their own applications on it. Or in our case, it might be multiple applications that we ourselves develop. So the approach, what it comes down to really for us is using familiar constructs. So we want to provide access control policy based on switch port and VLAN tag. These are all very familiar in layer 2 and simple things, right? And so in the OpenFlow world, they call that a slice. So our goal is to create slices on this network using things. There's an application called FlowVisor that might be something that you could provide to do slicing with. We're also looking at other things. But for us, the key is to have non-overlapping flow space so that we can avoid having one application disrupt another application that's controlling the network. One of the major concerns as we look into this and getting more serious about this, of course, is this notion of traffic engineering and where that occurs. So where we're at in the multi-tenancy space is, at this point, is we're looking at figuring out how to implement it. We'll be doing a lot of trials and whatnot with FlowVisor, but we're also exploring other options, including writing our own sort of flow space firewall, but then also figuring out how this might be used in conjunction with things like overlay networks to provide the appropriate level of simplicity, right? So when it comes to getting those domain experts involved, also there's a program that Internet 2, Juniper, Sienna, and Brocade have cooked up, where if you guys think that you've got an awesome idea how to help scientists move data on the L2S network, go to that URL and you can win some money if you're willing to, give up the code a little bit. So that's a program that we're trying to encourage people in our community to actually put some skin in the game and get emotionally invested and actually come up with those solutions, right, and figure out a way of helping people discover things. That's really what this is all about. So what I want to do now is talk about some of the issues and lessons learned. This is, if you Google sad monkey, this is what the cutest picture I could find. It's not all sad monkey, but it's been an interesting ride. And so the first thing I want to do is talk about availability. And so for the last 6 months, what we have, and I'm going to say this is also prefaces, I think this is different than the way that most people report it. This is the total availability, including disruptions during maintenance windows. It seems like a more absolute sense of how much disruption there really is. And on the average for all of our circuits, these 100 gig circuits, we're at about 99.96% availability right now in the last 6 months. And then for our nodes, we're at 99.25. So when I dug into those numbers a little bit, there's a couple things that stuck out to me. The first was that, in terms of our node availability, we had a couple instances where, for instance, we had a single instance where we had a 25-hour outage over a weekend and one of our nodes out east that was the result of sort of a combination of bugs in the switch implementation and the controller that caused it to basically stop forwarding things correctly. And due to the way we were monitoring things, the only thing that presented itself to our Network Operations Center was an ISIS adjacency alarm. So this sort of prolonged the outage because it was sort of misdiagnosed, which was, I'll get into that in a minute, but basically the lesson there is, it's tricky to make sure you've got the right level of monitoring and the right level of training, and this is sort of a growing pain there a little bit. And then on the circuit front, there are two things that have really contributed to those numbers that I saw. The first is that we are, for some vendors, having some 100 gig optics issues where the circuits flap periodically, and so that's contributing to the lack of availability. The other issue is there's been a lot of code upgrades on our optical systems as they go through, that these are being disruptive. So I would assume that those two things will subside as we get a handle on those. So vendor issues. Everybody talks about OpenFlow and how it's going to solve all the world's troubles. And, it's got some potential, and as Dave pointed out, it's got, you have to ask yourself if you're using, a hammer to hit a screw, right? But let's say you're hitting a nail with the hammer, and you're about to say, well, how is the hammer going to fail me? So a couple issues where this has sort of been pain points for us. The first is that for some vendors, they don't fully support the 1.0 spec, so they may match in layer 2 mode or in layer 3 mode, but they don't do both, right? Other vendors don't have proper barrier support, so that complicates the controller to switch communication. And then yet other vendors also have issues with not supporting all actions in hardware. So while it might do the right thing, it might not be able to do it at scale, so your performance envelope changes drastically, right? And then, of course, across all vendors, you see a variety of stability issues as their code matures. I'm not going to go into too many details, but you can imagine this stuff's bleeding edge, so we find interesting things, right? But on the performance issue, this is one that I think Dave touched on a little bit about the round trip times and whatnot. There's another issue here too, which is that a lot of from a black box perspective, the switch implementations aren't that performant, right? So, for instance, we've seen some vendors where the time it takes them to notice internally that they have a link that's gone down to the time that they actually start sending the packet to the controller is on the order of 1.5 seconds. That was quite shocking to us when we discovered that. We, of course, talked to the vendor, and they were very attentive at resolving that, of course. The next issue we have is that just about all vendors have a limited capacity for processing the instructions that tell it how to change the forwarding state. So these are the modify state messages, or flow mods colloquially. And for those, many of the vendors we interact with, they're constrained to about 100 flow mods per second or so. So you can imagine we're probably a couple orders of magnitude off of what many internal systems can do. And then the last issue we've got is the total number of supported rules. These are ranging anywhere on average from about 2,000 to 4,000, depending on which vendor you look at. So obviously, how you use this is going to be fairly narrowly constrained until they get that changed. Now, these are all things that, of course, the vendors are working on quite rapidly, right? So on the protocol front, there's a couple things I want to touch on. First is that the 1.0 spec isn't the best written spec. It's a great start, but the issue is it left a lot for the vendors to interpret. So that's the first major problem we've seen. The next is there's a variety of areas where it has inherent DOS risks. So, for instance, there's no real decent ways to do rate limiting between the control and the switch in terms of packet in or packet outs. And there's also not a lot of built-in mechanisms to help with table space exhaustion. So there's no way for the controller, for instance, to ask the switch, how big is your table, to ensure that we don't push too many rules and fill it up and have unpredicted things occur after that, right? And then, of course, in 1.0, there's a bunch of features that don't exist. These are all actually things resolved in 1.3 that make it difficult for us to implement the services we have today. And so those things include really no viable means for doing QoS, no TTL decrement, so you can't mimic routing, and there's no push and pop of VLAN tags, MPLS tags, or PBB tags. So the result is doing your pseudo wire kind of thing becomes sort of complicated, right? And then, of course, today, it was touched on by Dave, which was the round-trip time required whenever you need to react to a network event means that depending on where you place your controller and whatnot, there's some complications there. There are some features in the 1.3 spec, specifically the fast fail report groups, which should help with that in some limited cases. So testing in the last 6 months. So we're still working with the vendors it's a very active and intense interaction right now that we have. I mean, we're sort of in that bleeding edge state still. And anytime we get a new version of code, from a vendor, from ourselves, we have to basically put it through a full system test. And so in the last 6 months, we've had to do 6 release tests for vendors, and each one of those have averaged about 20 to 50 hours of engineer time. For applications, there's been about 4 releases. That's about 30 to 40 hours. And then we've also been looking at flow visor testing for different releases. It takes about 20 to 50 hours. The variability there depends on whether or not we see a lot of bugs or whether the release is fairly clean. So in all, that ends up being about 50% of our time is spent helping the vendors, and about, from one of my engineers' standpoint, it takes about 50% of my engineers' time to actually has been consumed with this testing. So the lesson learned for us there is, whatever guess of how much it's going to take in terms of testing, you probably need to double it. It's the classic software concept. But the thing we failed to appreciate when we went into this is that when you go into the SDN world, you also are taking on the responsibility of being the system integrator, and that really is the part where it's forced us to sort of kind of raise our game, but also means that our estimates on effort were a little bit off, right? So in terms of the management network, so if you're going to be looking to deploy your own SDN solution with OpenFlow, there's a couple of things you got to be cognizant of. In our case, our management network is the OSC channel across the DWM system. And so if there's a fiber cut, not only will it cause a topology change on our OpenFlow-based network, but it's also going to impact the management network. And so basically this means that we do use fail secure, so if we have a failure, we basically black hole traffic across that link, but everywhere else it continues to forward. But the issue is, your convergence there is going to block on your management network convergence, so you have to really think about that. And then, this is the part that they touched on also, which is distributed controller architectures can help potentially, right? Of course, you're going to have to do some routing protocol sort of replication conceptually to get those features. So if you are considering writing applications, my general sort of old man rant would be that robust WAN-capable apps can be kind of hard, right? Especially if you have to deal with restoration and topology discovery. There are reasons why, for instance, when you do IGPs and EGPs, you keep them separate, right? And I do question at times whether or not the majority of future WAN apps actually need to have full control of the interior path across a network. For instance, you might be able to just abstract that away and present these applications with a simplified backplane kind of construct, right? But if they do need to have control of the interior path, you have to ask yourself, do you trust the people writing those applications to do your traffic engineering? And if no, you have to think about how are you going to constrain bandwidth? How are you yourself going to do traffic engineering? And, so to keep those things in mind. Also keep in mind what you're going to do about network management disruptions and restoration performance. All these things, there are a variety of different ways, and it's all about trade-offs between performance, cost, and complexity, and a lot of testing time. So the future challenges for us are we want to work together with the community, whether it be the R&E community or the broader sort of Nanog community, to figure out better ways of testing OpenFlow applications and creating better testing regimens. We look forward to sort of getting our hands on viable 1.3 implementations because there's a lot of features there that we find exciting. And then in general, one of the challenges I see is that we really want to find a better ecosystem in terms of finding controllers that are truly distributed in the sense of that can abstract away the difficulties of message passing between them to sync that state, right? And then, of course, finding standard northbound interfaces that don't lock us in. So that's still something I think that's an open area. So these are the interfaces that an application developer would use related to the controller, not the OpenFlow spec itself. And then lastly, the thing for us to look at is refining our operations capability. I talked about sort of misdiagnosis and whatnot. And in general, the how do you monitor and how do you troubleshoot an OpenFlow application, or excuse me, an OpenFlow-based network is much more complex than your traditional networks, which have had years and years and years for us to figure out what the craft interfaces should look like and what those procedures are. So we're still working on those procedures and coming up with best practices internally. And that also relates to the the operations support team structure. People talk about DevOps. We're running into that right now. We've got a set of dedicated developers and we've got a set of dedicated engineers, and they work intimately together, but still organizationally they're in two different groups. And then lastly, there's this issue of if you are going to go after WAN multi-tenancy, you need to be cognizant of where you're going to do traffic engineering and how you can have the appropriate level of infrastructure control without causing undue disruption upstream to the applications that might be running on top of you. So, So that's all I have for you all. So any questions?
Dave Meyer, Brocade, UL. Hey, I was wondering, you mentioned FlowVisor and all the slicing stuff. I was wondering if you guys had been doing any work on 1.3, because for those folks who don't know, I kind of mentioned this in passing, but basically in 1.0 there was a pretty well-defined and well-understood notion of what a flow is. And so the flow space idea is built on that, right?
Right.
In 1.3 you don't have that anymore. Yep. And I was just curious if you guys had been looking at that or...
Yeah, so I've been looking at some. I think there's a couple things that of consideration, come to mind. At one level, what we're attempting to do is keep our slicing paradigm as simple as possible. So having a general arbitrary slicing across the entire flow space, I think, is going to be exceptionally difficult. Constraining it to say we're going to limit things to be just certain VLAN tags might be a solution. In an ideal world, what we would do is basically, present an overlay network somehow so that we can hide the complexity and sort of mimic and give them the presentation of an entire flow space so we don't have to slice it in a way that the application would need to know about.
Last question.
Jake Meckler from Dyn. I'm curious how you decide where your egress points will be for Internet 2 to primary Internet service, to egress to other providers?
There isn't.
Okay.
So we actually run a very constrained network. So most of our connectors actually have commodity internet connectivity on their own, and Internet 2 is a separate, basically you can think of it as a private network that can interconnects with other private networks that are research networks around the globe.
The reason I ask is we saw a major influx in DNS coming out of what appeared to be Internet 2 space. So I was just curious what, we can talk offline, I was curious what that might be attributed to. It was in the Ashburn area.
Yeah, we can definitely talk about it offline. We do have peering connectivity out there in Ashburn. So.
Okay, thanks.
Thanks very much, guys.